Right, so I have the live stream started on YouTube's side, and obviously the Google Meet has started as well. So we are ready to go. About 2 more minutes. Okay. Let me check the general channel. Oh, okay. There we go. And then back to today's channel. All right, good evening, everybody. It is Thursday, so we're getting close to the end of the week. Now that with the COVID-19 stay at home, I don't know how many people still maintain or keep track of uh, the day in a week. We do because we have a synchronous session only on Tuesdays and Thursdays, so we kind of need to track that. And I have another class on Monday and Wednesday as well, and then on Friday I got a whole bunch of meetings going. So I have to track the day of the week. But I think for people who take asynchronous classes, it's not as much. Days with class and days without class. And I think this summer class, because I'm teaching CISP310 in the summer too, this summer. Um, yeah, exactly. What is a Tuesday? Um, so that would be very interesting because as a summer session class, there are only 8 weeks to teach this class, so it's going to be very very compressed. Um, and as a result, the class is going to meet 4 days in the week, Monday to Thursday, every single day. So that's going to be intensive. Intensive. But apparently, some people want to get this class done over the summer. So, I guess I can understand that. Yeah, it is very intense. Just the guy who's teaching it, thinks it is very intense. All right, so it is time to get started. No, no, well, not my 440. So I only teach CISP 310 over the summer. Um, there's an interesting. This isn't something that's interesting because there should be the same number of people taking 440 and 310, but that really is not the case. Like 440 this semester, I have one class and it only has like about 30 people in it. But CISP 310, with I know it's a double lab section, but still, we should have about the same number of students. So I really don't understand why 440, doesn't have the same enrollment. So yeah, 440 can be taken before 310. 440 has a co-requisite of 430, so there's no interdependency between 440 and 310. So there's no reason why you cannot take 440 before 310. Some people choose to do it that way, and other people can take both in the same semester. So 400, yeah, I can see that. All right, so let's go ahead and get started with class. And today we're going to continue the discussion of D flip-flop. So I still have this page up, so I just need to click on it and then go to edge sensitive D flip-flop. Okay, so there we go. All right. Yeah, yep, I know. Yeah, taking both 440 and 310, in the same semester can be a little bit challenging, but at the same time, there actually is a few there are quite a bit of overlap between those two classes too. So it all depends on how people approach the classes. Alright, so getting on topic, we are starting the discussion of edge-sensitive D flip-flop. So instead of using Logisim to go through this one, I'm just going to draw the whole thing in on my tablet. So you cannot see the tablet because I'm just drawing, and I need to look at the screen when I'm drawing it. So you cannot see anything right now. So you might want to do something like this, on your own too. Maybe not now. It depends on how quickly you can get something done. So there's a data pin as an input. There's a clock pin being an input. Okay, so there are these two. And then we have, this is a little bit more complicated than the other one because we have two NAND gates. One is a 3-input NAND gate, and the other one is a 2-input NAND gate. And then there are two output pins, or just one output pin actually in this case, which is really just the data, which is Q. And yeah, the tablet is not showing. Well, if you guys want to see it, I can sort of show it to you. I think this might work. Give me a second here. So you won't be able to see the entire thing because part of it has to be off screen, or I can change the font size back to the default. Then I can put more of the tablet to the area that you guys can see. So you can see almost everything. No, you can actually see everything now. That's good. Alright, so that's better. Alright, so when I draw the pins, because I know the data pin goes into one of the input pins of N2, so we'll go ahead and draw N2 over here. And it's a NAND 2 gate, so it has got two inputs. And we can see that that this particular node here, I'm referring to this node here, is a very simple one. All it does is to connect the data pin into the second input pin of N2. So we'll go ahead and do just that. There we go. And then we move on to the next node. So this one goes from the clock pin to the middle one of N1. So let me label this. This is N2 and here is N1. N1 is going to be a little bit bigger because it's a 3-input NAND gate, and the clock pin goes to that. Okay, and then we also have S.R connected to the clock pin. So we have a SR latch. We call this S. The SR latch itself is called S, okay, even though it also has a pin called S. But in this case, we are connecting the clock pin, which is an input pin, to the reset of this SR latch. So there we go. So typically, this is just the way I usually draw my SR latch. Is the S pin is on the top, and then the R pin is at the bottom on the left-hand side. Alright, so we are now done with the second node. Moving on to the third node here. So this one takes the output of N2, connected to the second, the last, which is the third input of N1, but then it also connects the output of N2 to S.S. So there we go. This goes to here, but it also goes to here. There we go. And now we look at the fourth node. So in the fourth node, we take the output of N1 and then we connect it to the first input pin of N2. And then we also need to draw another SR latch now. So this is another SR latch. We call it C. So C.R connects to the output of N2. And the other one is, it also goes to the first pin of N2, first input pin of N2. Alright, so we can tap here and then connect it over here. So now we're on to the fifth node, which is this one, S.NQ, which is this one here, connects to the first input of N1. Alright, so yeah, I'm just thinking whether I should cross over pins or Y's or not. Let's just cross over. It's not too big of a deal. Oh, I take it back because it's supposed to go to... Okay, where did I make a mistake? Because the first Um, no, that's right. Okay, that is correct. Okay.
You
No, no,
connect
I made them. Yeah, go ahead.
N2 to the N1 out.
Yeah, so I think I made a mistake here. Okay, because N1 out is supposed to connect to N2 in 0 and not here. Okay, there we go. Alright, so I'm going to use a eraser. The eraser doesn't is not very fine, so it has sometimes most of the time it erases a little bit too much. There we go. Alright, so we are going to take the output of N1 and connect it to the first input of N2, which is here. So we take this out, connect it here, and it's also supposed to connect to C.R. C.R is here. Oh, okay. So that whole node is done incorrectly, I think. Okay, let me back up a little bit first. Yeah. Okay, let me back up and look at the output of N2. So the output of N2 connects to the third pin of N1, input of N1, so that's correct. It also connects to S.S, and that is correct as well. But this shouldn't be here, right? Alright, so now we move on to this one. We connect N1's output, which is here, to the first input of N2, so we got that. And we also want to connect it to C.R. So there we go. We tap it here, and then go to C.R. There we go. So now I think we're good. Moving on to the fifth node, S.NQ. Okay, so S.NQ is this guy. Goes to the first input of N1. Okay. Yep. Okay, so we are good now. We'll take it all the way around and connect it this way. And it also goes to C.S. So it goes to C.S, which is like that. And now we're on to the last one, which is pretty easy. We hook up the Q output pin from the CSR latch to the Q output pin. Alright, so just double checking. We do have some output pins not being used, and that's perfectly okay. Having input pins not used or not connected usually is a problem, but output pins, sometimes if there's actually no need to use it, you can leave it not connected. So we got two output pins that are not connected. S.Q, which is this one, is not connected anywhere. And if you look at the text description, it does not appear anywhere, so that's okay. And then C.NQ is the same way, which is the pin over here. It is also not connected to anywhere. Alright, so now that we got this picture drawn, what we want to do is to analyze the circuit. So I'm hoping most of you had a chance to read the text so that you know at least what the analysis is about. So the analysis is about if I have a rising edge, okay? Why is a rising edge going to quote-unquote store whatever the data pin, the input data pin is observing into the CSR latch so that the output pin Q is going to be the same as D, but only at that moment. Okay, so the analysis down here is basically following the propagation of changes. And that's something that you can kind of expect from your second exam. So exam 2 is going to have questions where you need to keep track of the propagation of changes dealing with circuits like a D flip-flop, an edge-sensitive D flip-flop, or a level-sensitive D flip-flop. So you might want to, you're just gonna try to do this on your own too, just to see, how to analyze the circuit. So what we want to do is we'll try again using, multiple layers, but I think this time it's going to work out okay because I got the base done already, and now I'm just going to insert changes to it so that later on I can reuse the same circuit. But I don't trust myself nor the tool. So I'm going to do one thing first. Give me a moment here. So I'm going to back up first. Given what happened yesterday, or in the previous class, we are going to copy and paste the design so that this way, if I cannot reverse, and erase, a layer and then go back to the previous state, at least I have a copy. I can just work with the copy later on. All right. So now we are better here. Add a new layer and go back to the tool. All right. So what we're doing now is let's see what happens when the clock pin is a 0 and the data pin is also a 0. So we are basically looking at the first step of 5.1. So in that case, we have a 0 here and we have a 0 here. So when I draw a 0 or when I write a 0, I'm basically marking a whole node, in this case of being 0. So right away, because this 0 goes to this NAND gate here. So if you have at least one input of a NAND gate being a 0, the output is guaranteed to be a 1. So we know the output is going to be a 1. And then the same applies to N1. So we know the output of N1 is also guaranteed to be a 1. So now we follow this change. Okay, so we follow this 1 here and see where it goes. So this one goes to the S pin of the SR latch. Doesn't really do anything. You need the input of a SR latch being a 0 to basically cause any changes. So this is not going to be a problem. And then the other way it goes is into the input of N1, but that's also not going to make any changes. There's basically this stops that particular chain of changes because N1 already has at least one of its input being a 0. So having some other pins being a 1 doesn't really change the output of N1 in any way. So we know we don't have to follow that change anymore. There are no additional changes caused by that propagation. So now we follow this one, okay, and we go, okay, it goes to the R input of the CSR latch. So once again, if the input is a 1, it doesn't really do anything, so we are not concerned about that. And then we also follow this and goes to the other input of N2, but since one of the input of N2 is a 0 already, so having the other input of N2 being a 1 doesn't change the output of N1, N2. So so that basically stops the propagation of changes. So now we want to see that there's a 1 over here and there's also a 1 over here. But we also want to follow the clock line. The clock line also goes into the R of the SR latch. So the 0 is going to appear here as well, which also means for the SR latch, we are resetting Q, which means we are asserting NQ. Okay, so this wire is now going to be a 1. Does everybody understand this part? Why, when we know the R pin of an SR latch being a 0, the NQ is going to be a 1. This is from the discussion of Tuesday. Alright, so what this one is also going to is going into the S input of the CSR latch. So as far as the CSR latch is concerned, it is only being asked to preserve its current state, which we don't know. Okay, so we have absolutely no idea of the state of the Q output pin at this point. We just know that when the data pin is a 0 and the clock pin is a 0, we're simply asking the CSR latch to maintain its current state. But we also know that the SSR latch, this one here, is going to have the NQ pin it's going to output a 1 at the NQ pin, because that's the behavior of an SR latch. Okay, when the R pin is a 0, NQ becomes a 1, Q becomes a 0, but we are not using Q at all in this case. So are we good with this analysis so far? I mean, all I did was to graphically show the first step when the data pin is a 0 and the clock pin is also a 0 initially, because we want to analyze what's going to happen when we have a rising edge. Basically, it means the clock goes from 0 to 1. Okay, very good. We got confirmation. Now we're going to change the input pin clock from a 0 to a 1. So we cross this out, we put a 1 here. So now we want to follow the changes. Okay, we want to follow the propagation of the changes. So the first change is going into N1. Nope, I take it back. So now this wire that was a 0, it becomes a 1. Now this is important because let's check what each wire is, or what each node has. This node here has a 1, but that node also goes to this pin here. So that means the third pin of N1 was a 1. Okay, we don't know whether it's going to change this at this point or not, but we know it is currently a 1. Let's check the other pin, which is this one here, the first input pin of N1. We track it down, right? And it is also a 1. So that means out of the 3 input pins of N1, 2 are 1s and only 1 was a 0. And that 0 is now changed to a 1 also. So that means at this particular instant of time, we have all 3 inputs of N1 being 1s. And because this is a NAND gate, when all inputs are 1s, the output become a 0. So that means this 1 is no longer a 1, it is now becoming a 0. So now we have to follow this change and see how this change from 1 to 0 is going to change the rest of the circuit. So we follow this wire and just basically need to understand where it's going to go. So the first place we track down is it goes to the first input pin of N2. Well, that's okay, because N2 still has the second pin being a 0, and it had it being a 0 to begin with. So that means the output of N2 is not going to change. So that's quote unquote a dead end of the propagation of changes. But it also goes somewhere else. This 0 also goes to the R pin of the CSR latch. So now it is going to affect the CSR latch. The CSR latch is now going to output a 0 for sure. Okay, so this is the analysis. Okay, and if you follow the slightly more concise version, which is basically just looking at the state of the output of the pins and how it affects the input of the other components and so on, it's really saying the same thing as what I just went through in this diagram. Okay, so we got several people typing, and we'll go ahead and wait a little bit. Okay, there we go. First question is, wait, why is the CSR latch outputting a 0? That has to do with the input pin R of the CSR latch is now a 0. And that is the behavior of a SR latch, is when the R pin is a 0, it quote unquote resets the Q pin. And so the Q pin becomes a 0. The next question is, when I'm propagating the changes, how are we deciding the order of propagation? So it's basically just following the changes. If you see a node changing, then you go to all of the components that can be affected by a change of that node. It gets tricky when you have 2 components changing things at the same time, but in this case we do not have that situation. If you have conflicting outputs, then you have a faulty design to begin with. Because conflicting output basically means one component outputs a 1 and the other component outputs a 0. So that's also called a fight. It's called a bus fight. You kind of imagine elementary schoolers, in a school bus and they're fighting. Okay, yeah. So it's called a bus fight, and a proper design should never get to the point where your two outputs are conflicting with each other. So that should never happen. Okay, so I'm just continuing to read the text channels. Did the N2 NAND gate change its output in this case? The answer is no, it did not, because the D pin is still a 0 in this case, and because N2 is a NAND gate, if at least one input is a 0, it's going to output a 1. So that's why that was a dead end of that branch of change propagation. All right, and okay, so and then Luke has a question. How did somebody come up with this? I do not know. I just know that people who come up with this type of design are pretty smart. I mean, it really is. It's not it's not straightforward. Okay, I do not know the process of designing these circuits. That's a very very good question. Alrighty. And then Victor is typing. All right, so I'm not going to go through 5.2, which is really kind of about the same thing, except this time the data pin is a 1 instead of a 0. But the whole point is, when you're dealing with an edge-sensitive D flip-flop, it only quote unquote stores when the clock pin goes at the instant when the clock pin goes from 0 to 1, and then when the clock pin is at a steady state of 0 or when it's at a steady state of 1, nothing happens. You can change the data pin all you want and nothing happens. Alright, so I'm going to go back to the text channel and kind of read a little bit here. Yeah, I like Omer's comment. Um, the reason why I cannot, yeah, exactly, because Logisim has internally, it does do the change propagation, but it is so fast that we cannot see it, nor is it displayed in the GUI. So that is why this is something that Logisim cannot show, is because internally it does all the change propagation, but it doesn't actually display anything at all. Well, okay, so the question is the SR latch always maintaining its state in the first step? Let's go back to the design, and the CSR latch is the one that is directly controlling the Q pin, right? So if the initial state of the CSR latch is both the S pin and the R pin being 1s, what do you think it's going to do to the SR latch? What do you think the SR latch is going to do when both inputs are 1s? That's something from Tuesday, by the way. So on Tuesday, we made a quote unquote truth table, and somebody commented on that truth table. And in the truth table, there's a notation called NC, exactly. And that kind of explains why initially the CSR latch is maintaining its state. You can also see even with data being a 1, we end up with the same scenario because C.S is a 1, C.R is also a 1, so C has both inputs being 1s, and as a result it is maintaining its current state. Alright. Depends, doesn't I? That's a little cryptic. It. Okay. Yeah, for a moment there I thought it was Yoda talk. Depends, doesn't I? Yeah, Yoda talk turns out to be postfix notation. That's one thing that I found out is it's just postfix notation. RPN, reversed Polish notation. All right. So I'm not going to do 5.2, and I'm also not going to do 5.3. Because the technique is the same. So this is something that you probably want to do. At least play out one of the scenarios. Okay, I know playing out all of the scenarios can be a little bit too much work, but playing out one or two, is good practice. Okay, because I want you guys to be able to follow the changes, follow the propagation of changes. But when we look at the circuit as a whole, okay, all that means is whatever the data pin has is not going to affect the CSR latch until and only when you have a rising edge at the clock pin. That is the essence of the edge sensitive SR latch. All right, so now we have two types of D flip flops already. I said SR latch, but I really meant to say D flip flop. Now that we have three different types of D flip flops, we kind of want to understand, why or how each one is different. I think we only got two. I excuse my mistake here. We only got two, not three. All right, so I'm going to the tablet again, and this time I'm just going to use the tablet to discuss the two types of D flip flops and how they are different. Okay. So now we have two D flip flops. One is what we call edge sensitive, which is the one that we just talked about today. It has got a clock pin. The other one is called level sensitive, and instead of a clock, it has got an enable pin. So the question is, why do we have these different mechanisms to specify when a D flip-flop should update based on the input pin D? Okay, because hey, if we have level sensitive, why do we have edge sensitive? How come there are two different types of mechanism? So to understand this, I kind of have to fast forward a little bit, to the design of a processor. So the design of the processor uses quite a bit of multi-drop, I should say, topology. So I'm going to show you what a multi-drop topology looks like. So imagine you have one input pin, and then you got a whole bunch of devices here, and all of these devices have some kind of input pins. So we'll call these input pins all Ds. Okay. And a multi-drop topology basically means one single input or one single node is connected to the input pin D of a whole bunch of flip-flops. Okay, a whole bunch of D flip-flops has the D, which is the input pin, connected to exactly the same node. So in this case, if the whole idea is, but I really just want this D flip-flop to change based on the data presented on the node, what are we going to do? Well, the enable pin is going to be helpful in this case, because the enable pin we can basically specify so that only the enable pin of this particular D flip-flop is a 1, and then all of the other D flip-flops would have an enable of 0. So the enable thing is a selection mechanism. It's kind of like in an orchestra, the conductor is pointing his little wind at a particular player and go like, hey, I'm talking to you here, you need to play a little bit louder. So it's a selection mechanism. Okay, we are basically saying we're trying to single out one particular component when every single component could be listening, but we are basically saying, but this is intended only for you. Okay, so that's what the EN is for. This is why we have level sensitive D flip-flops, is so that we can control which D flip-flop should pay attention to its input. Then why do we have clock, right? clock turns out to be a synchronization mechanism. It controls the timing of when the update should happen. So it doesn't quite control who should do it, but it controls the timing. So if in the same analogy, orchestra, okay, so the clock is analogous to how the conductor is waving his wand, but not pointing to a particular person. It's just providing the timing for the entire orchestra. Okay, and I still remember some stuff from my piano days. So if you're looking at the webcam, okay, I'm not sure whether you can see it very clearly, but when you have 4 beats, then you have to go like 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, like that. So that is the clock. Okay, it provides a time, and it provides a mechanism to synchronize updates, for components inside a processor. Or if you guys want a free music lesson or music theory lesson, I can incorporate more stuff, related to music. When I had to take music theory, I wrote a program that will give me all the scales. I just have to punch in the scale, and it will give me all the flats and all the sharps, of that particular scale. That was a fun program. Yes, it is indeed base 12. And that's very interesting because almost every music system in the entire world is based on breaking an octave, which is a doubling of frequency, into 12 steps. And that cannot be coincidental. That is just that just cannot be coincidental. So I just find it very, very odd that Western, Eastern, basically all kinds of music are based on this 12 semitone scale. So that's just it. Well, you guys did ask for a free music lesson, right? Okay, so I'm just gonna write down here. This is about timing. So one is about timing, providing a mechanism of synchronization, and the other one is providing a mechanism of selection. Okay, so they serve different purposes. And naturally, people will say, don't we need both at the same time? Just like the conductor of an orchestra, sometimes the waving of the wand is really just for timing, but other times the conductor would use his eyes, right, to stare at a particular section in the orchestra and go like, you guys, so don't we need both? Because we kind of need both, to make an ensemble work, and that's what a processor really is. Is an ensemble of a lot of components, and those components need to work together at the in synchronized steps in order to function. So we need both at the same time. So that leads us to the next design. Okay, so let me see what. Okay, I just found my mouse cursor. So this one I don't even bother to use a text representation because it's a little bit too much at that time, so I just copied and pasted the picture here. So this is called a clocked and gated, and gated means they're level sensitive. They're usually have the same meaning. So this one has got a clock, has got an enable, obviously has got a data pin, because the data pin is really it specifies the bit that we want to update the component to, right? Has got a single output queue, okay? But when you look at this particular design, it has got both. It has gotten both the enable and the clock. So the enable needs to be a 1, and on top of that, we have to see a rising edge at the clock in order for whatever the data pin has to update, in this case, SRC, which is the actual SR latch remembering the state of the D flip-flop. Okay, so the analysis is done here, a little bit. Okay, and the magic has to do with the AND gates. Okay, these are not NAND gates; these are just regular AND gates. So the regular AND gates, A1 and A2, really kind of do most of the magic. Okay, so the analysis of this, is uh, is documented down here. It's called a rising edge because when you look at the timing diagram, 0 is usually at a lower point and then 1 is usually at a higher point. So when you have an edge going from 0 to 1, it is usually called a rising edge. I can graphically show you. Okay, so this is a free lesson in circuit design. Seems you guys like free lessons, right? Okay, so we have voltage over time, or voltage or state. Okay, so a rising edge, if you look at an oscilloscope, okay, if you use an oscilloscope to look at the waveform, on a particular pin on an IC, an integrated circuit, this is what a rising edge looks like. Okay, it starts with a 0, and then at a particular time it goes, to 1, and that's why it's called a rising edge. Of course, the other one is called a falling edge, right? Going from a transition from 1 back to 0 is called a falling edge. All right. Oh, I thought Andrew was typing something. Just never made it here. Okay. All right. Let's move on. All right. So you might think, this is it, right? This has gotten everything that we have talked about so far. We started off with the design of a SR latch, and the thing about the SR latch is it's a very crude memory device. Okay, yes, it can remember a 1 versus a 0, but to change the state is really awkward. Okay, one input says, hey, if you make me a 0, I will turn the output into a 1, and then the other input says, hey, if you make me a 0, I will turn the output into a 0. We are only talking about Q, okay, because NQ is really the opposite of Q, so for the most part we only pay attention to the Q output. And also having both input pins being 0 is very unusual, so most of the time we don't encounter that situation. So most of the time we only have at the most one of the two input pins of an SR latch being a 0, and most of the time they should be both 1s, so we're just maintaining the state of the SR latch. So that's what the SR latch really is an 8 transistor simple design that can sort of remember a bit. Okay, that's all it can do, but it's really awkward to use. A regular D flip-flop, okay, the level sensitive D flip-flop, is for the most part just like a SR latch, okay, except that we break down so that we have a data input pin that specifies, do you want to remember a 0 or do you want to remember a 1. So now we have one single pin to specify what we want to remember, and then we have the other pin, which is the enable pin, to specify should we remember. Okay, should we change the SR latch to remember a different state. Okay, so that's our level sensitive D flip-flop, which is just slightly more complicated compared to an SR latch. And then we have the clocked SR latch, D flip-flop, sorry, D flip-flop. The clocked D flip-flop, has a clock line instead of an enable line, so that we can control the timing. Okay, when the clock goes from 0 to 1, at that particular instant we sample the D pin, and then we use that to update the final SR latch that is actually remembering the state of the D flip-flop. And now we have number 6, which is both clocked and gated. Okay, so it has a clock and also an enable line. So that should be it, right? Well, not quite. Okay, the problem with stopping here is when you first turn on a computer, what is the state of this SR latch here? The answer is we don't know. We really don't know. Okay, because we started our analysis of, hey, okay, let me see. On Tuesday, when I first used my own SR latch, you remember that the outputs were initially red of that SR latch, and that's because when the inputs are 1s to begin with, the SR latch really doesn't know what state it should be in, and as a result, we when the computer first starts, there's no control over the state of its registers, the registers inside the processor. RAM is another thing. Okay, we can afford to have RAM uninitialized. It can be all jumbled up, a bunch of zeros, a bunch of zeros, and a bunch of ones, at random locations. That's actually okay. It's not a problem. But registers inside the processor is a whole different story. They need to start with a known value. So that is where we got our last detail. Okay, so the last detail is to add this little line here, this note here called reset. So the reset line, when it is a 1, then it will bypass the whole mechanism of clock, enable, and stuff like that. Whenever the reset line is a 1, it will instantaneously change the D flip-flop to a 0 in this case. Okay, no questions asked. It doesn't have to be enabled, doesn't have to have a rising edge. It would just say, nope, you're going to a 0 at this point. And this is really important because when in a real design, in a real processor, there's actually a reset line. The reset line goes not only into the processor, but it also goes to all the peripherals on a computer. On a PC, so that means it also goes to the PCI bus controller. It also goes to all kinds of controllers. Okay, the north bridge, the south bridge, blah blah blah. They all receive the system-wide reset signal, and it stays on for a long time too. It stays on for probably a good fraction of a second. Yes, I know fraction of a second doesn't say much, but I would say it's at least 1/4 of a second, if not more, which by comparison to the clock speed of a processor, that's like a long time, right? Um, when the reset line of a system is held, or when it's asserted, all the components reset. It's a hard reset of all the components so that they all go to a default known state. And in this case, this particular mechanism, by using this OR gate and this AND gate over here, we are basically forcing this particular SR latch to be a 0, to output a 0 at Q when the reset pin is a 1. So that's our reset mechanism. So you might say, okay, I think we can rest now, right? Nope, we have one more slide to go, one more picture to go. So because this mechanism, the mechanism in section 7, can only remember 1 bit, okay? And 1 bit is, sometimes it by itself 1 bit is already quite useful, but most of the time when we want to represent numbers, where in memory we should get the next location, that sort of stuff, 1 bit doesn't really quite get the job done. So that means, we might want to, instead of remembering whether it is a 1 or a 0, we might need to remember an 8-bit number, a 16-bit number, a 32 or 64-bit number. So that's what the next one is it is really just stacking, this design here. So imagine this design, with a box, and becomes just a component inside a larger design. This is how we can make a multi-bit register. So the multi-bit register has a whole bunch of multi-drop connections. So let's take a closer look at what is multi-dropped and what is not multi-dropped. Okay, so you can see the clock is multi-dropped. This is the clock, and you can see how the same clock goes to the clock of this D flip-flop, goes to the clock of this D flip-flop, because they're all coming out of the same node. The enable, same way. Okay, so in this case, the enable is also going to every single component. And yes, I did say earlier that the enable is used for selection, but we are treating all 8 bits here as one single thing, and that's why they all share the same enable. Let's see. The reset is another one that is multi-dropped. So when you look at the reset node, it is also shared by every single D flip-flop in this design. So what is not shared are the bits coming out of the D input pin. This is an 8-bit input pin, and this is the output Q, which is also an 8-bit output pin. So these bits are not multi-dropped. So bit 0 only goes to the D flip-flop responsible for bit 0. Bit 1 only goes to the D flip-flop responsible for bit 1, and the output is kind of the same way. The output of the D flip-flop only responsible for bit 0 would only contribute to bit 0 that eventually becomes bit 0 of the output pin Q. Alright. So are we good so far in terms of understanding the concept of a register? Okay, very good. So what we'll do next um, is to build some really elementary circuit using registers. Okay, because what you see here, if you put a big box around this entire thing, it is called a register. Okay, so we want to build some really simple things, but hopefully a little bit fun out of the concept of a register. And I'm just checking to see if I still have my Logisim up, and I do not. Okay, so I'm gonna start a new Logisim instance. There we go. Alright, so where's my mouse cursor? There we go. Alright, so we'll build a simple circuit. If you have analyzed one of the very first circuits that I gave you guys, but not required for your homework, you might have seen this a part of this design already. But now we're gonna make good use of it. So what we'll do is we go to memory, and instead of picking out the flip-flops, which are very simple devices, we just pick out a whole register. And then we slapped the register into the design here. And then the first thing we want to learn about the register is what are the interfaces? Okay, how does the outside world interact with a register? So it's got a bunch of pins, right? So it's got this D pin, which is the same as our D pin. This is where the data is coming in. It's got the Q pin, which is the output of the register, and a register always outputs whatever it has in the content, and which is what the 00 is. So the 00, if you change to the poking tool, you can actually change the 00 to whatever you want. Like you just overtype it, okay? Just type like 4E, and it becomes 4E, which is in binary 00. Excuse me, it's 0100. 1110, okay, but it's in hexadecimal. Okay, so we have some of the components identified, or some of the interfaces identified. Then we got this enable pin, okay, which is basically the same as our EN. The clock pin doesn't have a name. It has this kind of weird looking triangle thing. That is a fairly widely used industry standard to use a wedge or a triangle to indicate this is a clock pin. It has one pin that is labeled 0. That's our reset pin. Okay, the reset pin or clear, so analogous, same thing. When this pin is a 1, then the content of the register will reset to 0. So this is what a register looks like. You can change a few properties of a register. You can change the width. So instead of being an 8-bit register, you can change it to a smaller number of bits. You can also change it to a wider register. For the most part, for our toy processor, we're only making use of 8-bit registers, except for one single component in the processor. We'll get to that in maybe a week or two. You can also change the trigger of a register. Rising edge is the default, which is what I explained in my notes. But rising edge and the falling edge can easily be interchanged because you just need a NOT gate in front of the clock to change it from a rising edge to a falling edge register. So that's a fairly easy thing to do. You can give it a label, which is really just for display purposes. Okay, it doesn't really change the circuit design itself in any way. It just makes it easier for us to visually identify which register is which. Okay, so that's what a register looks like. And what we'll do next is to grab an adder. Okay, so we'll go to arithmetic and grab us an adder. There we go. And the first thing the only thing you can configure with an adder is how wide it is. Okay, so we want the adder to be 8-bit wider. Okay, so that's it. Now what we're going to do is we are going to hook up these two components. Okay, so with an adder, it has got 2 pins to specify what number we are adding. So we'll take one to connect it to the output of the register. There we go. And we'll hook up the other one to a constant of 0. So if you go to wiring, okay, and you go to constant, you can now specify a constant in any width because you can change the data bit width here. So this width has to match where the constant is going. And we also don't want the value to be FF, we want it to be 0, 0. So now you're going to say, Patak, it's useless to add 0 to anything, you just get whatever that thing is back. You're absolutely correct. And that's why we also have CIN, carry in. So carry in is what we know as K0 when we talked about the carry look ahead mechanism. Remember K0? Remember a lot of people ask, what should we do about K0? Should we assume it to be 0 or what is it? So when we did the circuit design for carry look ahead, you remember the K0 was an input pin. This is why it is an input pin, because this allows us to daisy chain adders. So if all you can do, if all you can afford, okay, is to make 8-bit adders, but you really want to add 16-bit integers, now you can daisy chain 2 8-bit adders to become a 16-bit adder. It's not quite as fast as a true 16-bit carry look ahead adder, but it is not bad. Okay, it's just twice as it's basically it takes 2 propagations. It takes the first adder to finish its calculation, and then it takes the second adder to finish its calculation. So it's a good trade-off in that case. So this is where we're going to hook up a 1. Okay, so we go to constant again, and then we specify a 1-bit 1 because carry in or K0 is a 1 single bit input. So now we are basically just saying add 1. Okay, that's all we are saying. Now if you are saying, but heck, we could have made K0 or carry in a 0 and then make this one a 0, 1, as a 8-bit integer for 1. Yes, we could have done it that way too. Yes, absolutely, we could have done it that way. So now what we do is we take the output. So this is the sum. Okay, the output is the sum of the 2 inputs along with K0. And this one is carry out, which is what we know as K3 when we had the homework assignment on carry look ahead mechanism. So we are not going to hook it up to anything because we are not daisy chaining, the adders. So we'll leave this one unconnected, which is fine. But we'll take this one and then we'll take it back into the D input of our register. So I'm going to leave it unconnected right now. So the question, or what I want you to think about, is what happens when I do complete this circuit, right? Because would this register just go crazy and just keep adding 1 to no end, or what is it going to do? Okay, so let's find out. Okay, let's find out what this circuit is going to do. Okay, absolutely nothing. It's going to do absolutely nothing. Well, that's because we haven't really specified the enable, and we really haven't specified anything about the clock. Now the reset, yeah, well, if you want to play with this, fine. Okay, you can play with it using in wiring. It has got a really interesting tool called a button, or I could be wrong because it might be somewhere else. Okay, maybe in input output. Yeah, so in input output, it has got a construct called a button, and the output of a button is on the east side. Okay, so a button is kind of like an input pin, except it's a push button. Okay, when you don't push it, it is a 0. When you push it, it is a 1. That's it. Okay, that's basically what a push button is. So if I can illustrate how it works, right here, you change to the poking tool. So the moment you poke it, it becomes a 1, and then it resets the content of the register. Okay, so that's it. That's what a push button is. We can, as far as enable is concerned, we can enable this all the time. So I'm just gonna hook up the 1 directly to enable. So this register is always enabled. And somebody's gonna say, but that's gonna make it go crazy. It will just go to 1 and then go to 2. It doesn't know when to stop. Nope, nothing happens because we don't have a rising edge. Remember, this is it's based on D flip-flops that are both gated and clocked. Okay, so as far as the gate is concerned, it is saying yes, go ahead and update, but we are lacking the other component, which is the rising edge. Okay, so for the rising edge, we're going to hook up to yet another new component that we haven't really used before. It's called a clock pin. Okay, and if you look at the outline of the clock pin and you look at the design of a clock pin, it's like, well, Tech, isn't this just a fancy looking input pin? Especially after we hook it up, and absolutely nothing happens. Tech, I feel cheated. You could have just used a regular input pin that displays 0 or 1. Okay, so how do we change the clock pin? You poke it. Okay, so once again, you poke it, and you go like, hey, something is happening to the register, and happens again, and again, and again. What is going on here, right? Well, remember this is an edge-sensitive D flip-flop, right? It is enabled already. So as far as being gated, that's not a concern anymore because it is always enabled. But what it is not is always clocked, because clock cannot be always, okay? Because it is it's a transition of a 0 to a 1. So what is happening at this point using the poking tool is really helpful, is you can follow this wire. This wire has 04 in it, which makes sense because it is the output of the register, and the register clearly has the content of 04 in hexadecimal in it. So when you look at the behavior of the adder, we're adding 1 to 04, so the output of the adder should be 05. We poke it and it says, yes, we have 05 on this wire. Then how come the register is not changing to 05? How come it's maintaining as 04? It's because we don't have a rising edge yet. Okay, the clock is 0 at this point. Now how do we know the clock line is a 0? Well, you can poke it to see it is a 0, but you can also tell from the color, because the color is a dark green, which means it is a 0. If it's a light green, it is representing a 1. Okay, I'm guessing most of you have already observed this in Logisim already. Is a light green means a 1, a dark green means a 0. Okay, but when I poke and change the state of the clock, and it toggles from 0 to a 1, then we have a rising edge. And at that moment, okay, right at that moment, the input of D is used to update the internal state of the register, so that it becomes, oops, okay, click on the wrong location. Then it becomes a 05. Then somebody's gonna say, but why is it not becoming 06 and 7 and so on now that it's updating? Well, because the edge has stopped. We created a single transition. We created a single edge from 0 to 1, and now we don't have any edges, right? Now it's steady state. So at a steady state, the register is no longer updating. Okay, it's basically ignoring the input, even though it is enabled. Okay. So okay, let's get back to the earlier question. The earlier question was, we could have used just a regular input pin. Why use a clock pin? So the clock pin is different because you can go to simulate and use these keys, okay, because a clock pin can provide ticks. So you can basically use Control T to have a single transition. A single transition means it goes from 0 to 1 or it goes from 1 to 0. Either one is called a transition. But you can also configure the tick frequency. So right now it's at 8 hertz, which is great for demonstration purposes. And then you can go ahead and enable ticking. Okay, this is automated ticking, so I'm just going to enable it. You can see now it changes automatically at 8 transitions per second, which basically translates to 4 rising edges per second. So the number is incrementing at about 4 times per second at this point. And you can always stop it too. You can either use the hotkey or you can go to simulate and then just click tick enabled so that the check mark is not checked anymore. Alright, so are we doing okay so far with this particular design? Does everybody understand the whole concept of using an edge, a clock, to specify when a register updates? Cool. Okay, I'd like to see all that. It's getting spicy. Which is a good reminder for me to drink more coffee. Alright, so here's a question. Why can't we change the value if the enable pin is a 0? If the enable pin is a 0, we cannot update it. It is a 1 at this point. How are clocks made to operate at a certain frequency? That's a very interesting question. I can answer that question. CAN can answer that question, but only in a superficial way. Okay, EN is connected to 1. Yes, that's exactly. So that answers the earlier question. Okay. Nope, the button is connected to the reset or clear pin, not connected to the EN pin. Okay, so we still got a few questions coming. So what happens when I click the button? Which button? You mean the reset button? The one that connects to the reset, like this one? Yeah, the button. It will change the content of the register back to 00, like that. Yep. Which is exactly what the D flip-flop that I demonstrated earlier would do, because it is independent to enable and the clock. It just goes straight to the last SR latch inside that D flip-flop. Yep, sure. Yeah, you can build it and play with it. I mean, I really encourage people to kind of build about the same circuit and play with it, because one, it kind of keeps your Logisim skill, up to date, kind of refreshed. But the second thing is, when you build it, I think it makes new neural pathways in your mind, in your brain, and it connects the concepts. In addition to what you have just connected, based on listening to me and watching me do this experiment. When you do it yourself and when you create the circuit, I think it helps to build more connections within your mind. So I think it's a good idea to do it if you have the time. Okay, that's a good question. So Alfred asked, if we just let it keep going, what's going to happen? Because at some point, the 00 is going to become FF. So when you add 1 to FF, what's going to happen? So that question can be answered by your own design. So in your own design, remember, in your own design that you have 3 bits, right? 3 input bits. X has 3 bits, Y has 3 bits, and then you have K0, right? So I want you to do the same thing, okay? In your own design for the adder, specify X to be 1, 1, 1, okay? All ones for X, 0, 0, 0 for Y, and then a 1 for K0. That would basically replicate exactly the same situation that we would run into, except with fewer bits, okay? Then what you will observe, I can tell you the answer already, what you're going to observe is that the sum is going to be 0, 0, 0, and then K3, which is our C out over here, is going to be a 1. So let's try that, right? I mean, let's play with this. So we'll go ahead and reset the clock back to 0 so it doesn't update, and we can force a value into a register by just clicking on it and then type FF. Okay. So now we have the output of the register being FF, all ones, right? And now we can check what is the output of the adder. The output of the adder is now all zeros. And then C out, I don't even need to click it because you can see it's a light green color right here at this pin. Right here, right? So you can see it. So we know, it's not going to cause a problem. It simply has to do with how we define, K3, in our case. K3 is really just based on a whole bunch of AND gates and whatnot, and so are the sum bits. And that's why it's not going to cause any error. Okay, it would just do whatever the logic gates is supposed to do, give us all zeros for the sum, and then a 1 for the overall carry. What did I do to change the register? Click on it and type. So I think you have to use the poking tool first, and then you click on the register, and then you just type over it, like 0, 0. You have to type two keys because there are two hexadecimal digits when you have an 8-bit register. Yep. All right. Cool. All right. So this is a pretty simple, mechanism, and now I will give you a picture of the toy processor, and then we'll go back and explain the other components because I want to give you a context before I explain, the other components. But for the most part, the most complicated components are done already. But when you look at the design, you would probably disagree. But then I'll explain to you why those other, components are not really too big of a deal. All right. So what we'll do is we're gonna open up the toy processor design, and it is in my documents folder under CISP310 processor 0003.circ. There we go. Alright, so now what we are looking at here is the toy processor design. Here we go. And oh, one more thing, in case anyone has forgotten, the zoom control of Logisim is all the way down here. People, sometimes ask me in the middle of a semester and ask, I can't see the whole thing. Well, the zoom control is over here. So this is the toy processor, which is a fairly simple processor. It is, it definitely uses the RISC philosophy. When I designed and designed this processor, but it's not 100% RISC. Okay, RISC. I'll explain that term later. But I do want to point out some of the important stuff in this design. Is most of the things that are really complicated we have talked about already. And some people would say, but we haven't really talked about this thing over here. What is a multiplexer? Or this thing over here, what is a demultiplexer? What is this thing over here, which is RAM? And what is this thing over here, which is ROM? Okay, those are the only 4 components that we haven't really talked about, and they are super easy by comparison to explain. Okay, what we have already explained are the registers, and we have plenty of registers here. So we got one register here. We got one register down here. We got another register here. Another one here. And then we have 4 more registers inside this thing. So inside register bank, we got 4 more registers. They're simply named A, B, C, and D. And then we got this ALU, which inside there's an adder, there's a subtractor, and there are a few other things. But we have already talked about adding and subtracting in base 2, right? The carry look ahead mechanism and also the borrow look ahead mechanism. So we have talked about a good portion of the complex stuff already. And I know someone is still getting stuck with the idea of, but we haven't talked about this or this. Okay, what is a multiplexer and what is a demultiplexer? All right, so that's going to be what we'll be explaining. I guess for the rest of today's class and also going to be next Tuesday. Um, so we'll start with the simple stuff first, okay? And I will also show you how you can look up things by yourself and kind of learn about these things by yourself too. So when you click, not using the poking tool but using the pointing tool, so when you poke or when you click on a particular component like this one here, it will tell you what it is. It tells you it is a multiplexer. So once you know the name, you can look for it. So what you want to do is to look into help, go to library reference, and then go to plexers. Okay, so in with multiplexers and demultiplexers, they're both in the plexers library. You may not be able to see the whole thing. There we go. So they're both in the same section in the help file. And yes, so MUX is for multiplexer, is the abbreviation of multiplexer, and then DMUX is the abbreviation of demultiplexer. So now we go to here, and you can see we have the help for multiplexer, and then we also have the help of demultiplexer. So what exactly are these things, right? I mean, you're killing me. You keep telling me I can just look it up, but you don't really explain what it is. Well, they are basically just like railroad switches. So what I'll do is I'm switching to the tablet at this point. I mean, if you know young children at this point, and they are playing with the Thomas the Tank Engine toy set, you can borrow their pieces, and you can just say that I kind of need to borrow this, for one of my classes at a college level. Yes. Okay. So with railroad switches, okay. So let's just say that we have this is a rail, okay, a rail, and it's coming into a junction. And let's just say that there are 4 exit points, okay. Well, let's do 2 first, okay. 2 is easier. So we have one track or one way to continue, and then we have one to just branch off here, okay. So we want to make this happen. We want to be able to direct a train. So the train is coming in this direction, and we want to be able to direct the train and say, sometimes I want you to go to, option A, and other times I want you to go to option B. So this particular piece here is called a switch. I mean, literally, it's really just called a switch. And the mechanical component to make a switch is really kind of easy. It really just kind of okay. Instead of me describing it, which I'm not very good at, we'll just look it up. Okay, so we look up railroad switch, and here we have a picture of that. And let me see if I can get a good image. But it also shows the switching mechanism itself. I think there was one earlier that shows the mechanism. There we go. And let's see, is it playing?
Let's see how it works. In this system, wheel and rail, which play an important role in the track change process. The inner rim of the wheel, called a flange, is comparatively greater in diameter than the outer part, which prevents the wheel from sliding off the track.
There we go. And I know you guys are saying, how come our classes don't come with mesmerizing music like that? I don't know. trademark issues, copyright issues, maybe. But anyway, so now we have looked at a physical mechanical switch. Okay, so the next question we need to ask is, what is, so if somebody is here at the switch, pulling the lever, okay, what do we need to signal that person and go like, we want option A versus option B in terms of how many bits of information is there? So, question. Okay, so let's answer that question first. In terms of, it's exactly, okay, Nicholas has nailed this, okay, 1 bit, okay, we need one single bit, so that it's a 0 means, we want to keep, okay, let me switch back to the tablet, so we can, you can label it either way, okay, but the idea is we will label one option as 0, we'll label the other option as 1, okay, which one you want to call as a 0, which one you want to call as 1, it doesn't really matter, okay, it's just that one single bit is enough to specify this, okay. Okay, isn't that cool? Easy peasy, right? So this is basically the same as a, let me remember, this part is, I can never remember this part, which one is a multiplexer and which one is a demultiplexer. This is a demultiplexer, there we go. So this is a demultiplexer, where we have one bit coming, where we have an input, okay, which is analogous to this arrow here. We have two possible outputs, which is corresponding to option A and option B. So we'll label option A and option B. And then we have a control mechanism here. Okay, so we have a little lever control mechanism here that is known as our selection. Okay, so the selection always has a little gray dot on top of it to signify that this wire, this little wire over here, is the control mechanism. So in this case, it only needs 1 bit to do it, right? So 1 input, 2 outputs, and then 1 more wire to control, to specify, where should I connect the input? Should I connect the input to A, or should I connect the input to B? And that is specified by the selection bit. Okay. So now the question is, well, two-way switch is cool, but what if I need a 4-way switch? What are we going to do with a 4-way switch? Okay, so Marco is getting it, okay? Because if you think about in the real world, okay, a train coming in to a particular place might need to go to one of 4 possible destinations. I mean, that can totally be, you can totally imagine that can happen, right? Especially when this particular place is at the hub of some transportation warehouse. Okay, so one input can connect to many outputs. So but we are not concerned about 8. We're only concerned about 4 at this time. And then I tell you, hey, this mechanism here is the only mechanism that you can use. Then you go like, oh man, we are stuck. We're only stuck with 2 outputs. No, you're not stuck with only 2 outputs, because I would also say, but you can stack these designs. You can plug and play. They're like Legos, right? Yeah, I know. In about 10 years, I can mention the word Lego, and nobody knows what I'm talking about. So, what is Lego? Lego, what is that? What do people do with these plastic pieces? They make no sense. Alright, so this is the last topic of today. I know we are almost running out of time, but I do want to get this point across, because physical Minecraft. Tell that to the kid. It's like, I'm taking your computer, but I can give you physical Minecraft called Lego for a week, and see what happens. I can assure you nothing pretty is gonna happen. That's what's gonna happen. Alright. So what we'll do is we're gonna say, we only have the basic mechanism of a 2-output demultiplexer. But what we can do is to connect the output of this one to another 2-output demultiplexer. And by the way, this is the first time in the history of me teaching this class using this way of explaining how to make a four-way switch only using two-way switches. So now we have A, B, C, and D. Cool. Okay, the train is still coming in, from this end, but it can now, in theory, be going out of A, B, C, or D. But the problem is, what about the control signals? Because each control signal, which is one is here, and one is here, each one can only take one single bit. So how do we do this? So we'll call this control signal X, and we'll call this control signal Y, and we'll also call this control signal Y. The reason why we can use Y twice over here is because they cannot be both useful at the same time. Because if X is specifying the top one, that means the bottom one is not in use anymore. So however we switch, this bottom, the third switch, doesn't really matter. So now we try to create a table. We got X, we got Y, and then we got destination. Okay, so we make a simple table out of this. There are only four destinations. We have destination A, B, C, or D. Alright, so now I need to assign certain things, right? So we'll say this is output 0 and this is output 1. Okay, in other words, if X is 0, the input goes to output 1. If X is 1, the input goes to output 1. So that's kind of the standard. So now we say, okay, if we want the train, which is coming in always from this direction, to output at A, we need to follow output 0 from the first switch. Okay, so that means we need a 0 here. But once the train appears over here, we also want output 0 in order to specify to get to destination A. So we have 0 at 0. What about destination B? Okay, we need X to have a 0 as a control signal, and then Y needs to have a 1 as a control signal. 1, 0, and then a 1, 1. Woohoo! Yes! So now we can say, but Tech, you still don't have a four-way switch. You now have a stack design of 3 two-way switches. Then I go like, wait, hold on a second. Let me. Oops. Oh, what just? Oh, that means I pinched. I used a pinch. So it just magnified. That's all. Okay. So now let's go ahead and draw a box. Okay. So we're gonna draw a big box, and I have to be careful where the boundary of the box is. And then I take X. I take Y to be over here. And I say, hey, look at the big box here. Now we have a four-way switch. Do we have a four-way switch? If you look at it from the big box perspective, we got one input coming in. We have 4 possible ways of coming out. The only thing that's kind of tricky is now we need 2 bits to specify which one of the 4 output the train is going to be coming out of. That's it. Now we have a four-way switch using 2 input bits. So the next question is, how do we make a 16-way switch? Yes, most of you were thinking about 8. No. 8 is too easy. Let's go bigger. 16. So why do I mention 16? Because now you can hook up A to another four-way switch, B to another four-way switch, C to another four-way switch, and then D to another four-way switch. So now we have a 16-way switch. And then you can have the next up is going to be 16 times 16 and so on. So you can basically stack these designs to have one input, and then you can specify which output the input is connected to. What about the rest? The rest are simply not connected. No train is going to be coming out of track B, C, or D if you have selected the train should be coming out of track A. The reset Oh, the reset is already explained in the notes, I believe. So that's it. That's it for today's lecture. There's no new lab except for the one that's due on Tuesday, which is the positive exponent, I guess, programming assignment. Um, so that's the only one. So let me answer the question. Oh, okay, there's one more question. So the multiplexer and demultiplexer. Oh, okay, so I have just explained the demultiplexer. So this is a demux, right? So now the question is, what is a multiplexer if this is a demultiplexer? The directions are opposite, okay? If you get rid of the D, if you have a multiplexer, that means a train can be coming in from one of the four, and then it's coming out of the single end on the other side. That makes it a multiplexer. That's it. That's the only difference between a multiplexer and a demultiplexer. Unlike a real-world railroad switch, um, these switches in an electronic circuit, they are not bidirectional. So if you have one input, multiple output, it's called a demultiplexer. When you have one output and multiple inputs, it becomes a multiplexer. That's it. I mean, that's the only difference between a multiplexer and a demultiplexer. Yes, exactly. So Luke is correct. So with multiplexers, basically, you basically specify either one input track, one train coming in, and you decide which one of the output tracks is going to be going out of, or you can have multiple trains coming in, and only one train is allowed to get out. Okay, and basically you're selecting which train that is sitting at the entry point can go through the switch to connect to the output track. It's more like a mirror. So to answer Nathan's question, it's more like a mirror. It's just a direction thing. Are we talking about one input, multiple output, or are we talking about multiple input and one single output? Yeah, so it's time to get some orders going. So let me show you what you can do with this. If you want to explain this to like a 5-year-old, you can order Thomas Tank Engine switch pieces. And these are not actuated, but they do have actuated switches too. So let me look for those. Actuated. There we go. So this piece here, the one with a yellow thing, that one is an actuated switch. So if you really want to get analog, you can you can get a whole bunch of tracks like these, and then just get a whole bunch of these little little cars, and I mean the processor really is a lot of stuff like that. I mean there are registers too. Registers are basically places where you can store something. But when we look at the transmission of data, we are really looking at trains, carrying something from one place to another place. Yes, I can actually hear the theme music of Thomas the Tank Engine in my head right now. Yeah, that's the downside of having uh, an Alec Mobile kind of mind. I'm not sure how long it's gonna take, or how to capture that in a Google Doc. Maybe you can make a movie, like a YouTube clip of you, working on these pieces, and then submit the YouTube recording. That'll work. A demultiplexer. Yeah, sort of. Yeah, you can also think of these as what we used to call KVM switch. KVM stands for keyboard video mouse. So this way, you can use one set of keyboard, one keyboard, one mouse, and one computer. Is it the other way around? No. One keyboard, one mouse, and one monitor, and then you can select which computer you connect those devices to. So it's kind of like a KVM switch. Yeah, I'm not sure whether those things are still really usable or not, because a lot of smart video cards can detect whether it is actually connected to a monitor or not. And if it is not connected to a monitor, your operating system may do certain things, and then when it reconnects, it may not resume the same state. So that's the problem with modern day computers that are really smart. I mean, they know, whether they're still connected to a monitor or not. All right, so let me get back to the earlier question, because there was a question about how reset works on the circuit. So I'm not really sure which circuit we are talking about. Are we talking about the circuit that I have displayed in Logisim, or is it the other one? I mean, are we talking about this circuit? If we're talking about this circuit, it really is just the property of a register. When the reset or the clear pin becomes a 1, it will just change the content of the register back to 0. That's the behavior of a register, which, by the way, you can also find in the online help. So getting to know the online help is really going to be useful. Alright, so I think all the on-topic questions are answered. Very good. Okay, got it. Okay, very good. Yeah, Raspberry Pis are really useful. They're truly useful. I was telling people, because there was a discussion of the inequity when we are going 100% online, where some people cannot afford to buy a new computer to go online to take classes. And I was saying, hey, you can use a Raspberry Pi. And then everybody looked at me, just go like, what are you talking about? Then I just kind of shut up. Because I didn't want to get into like, oh, you can run Linux and open source and all kinds of stuff like that. Yeah, no. Not going there. Yes. Alright, so I'm gonna turn off the live stream at this point. I'll still keep an eye on the text channel. So I'll shut down the channels one by one. There's like 3 things to shut down. So the first one to go is Google Meet, and